Welcome to March. It's about time. It's been a year. At any rate, one of our last big topics, in fact, it's our last toughest topic in the mechanics course this year, is rotational motion. Rotation around a rigid body is what it's called in Chapter 12. There's a lot of examples I have. I'm going to share my notes with you. I'd encourage you to look at those. There's examples in the book also. I'm going to go through a select few of these in this Ed puzzle. And this way, at least I'm going to explain some of the big ideas. I think try to as many as I can. Do an energy example, a torque example, maybe a parallel axis theorem example. So the first thing to think about, I don't think you'll ever have to memorize these, but it's still good to know them. The moment of inertia, which is the equivalent for mass, when we talk about rotating things, symbolized by the letter capital I. For a solid sphere of uniform density, it's 2/5 mr squared. For a hoop, meaning that all the mass is on the outside, it's mr squared, which makes sense because the mass is all at the full radius out. The solid disk has a moment of inertia of 1/2 or 0.5 mr squared. The interesting thing is the way that these are derived is from integral calculus. Hopefully that kind of makes sense from looking at some of the 1/2 something times something else squared. And we may get into that a little bit, we may not. But right now, those are things that are useful to know. Another thing I think is really important out of this chapter is the parallel axis theorem. It basically says, how can you figure out the moment of inertia when something's not rotating about its center of mass? It makes sense that it's going to be tougher to rotate something if it's not rotating about its center of mass, but how do you mathematically figure that out? Well, first of all, you figure out what the moment of inertia would be about the center of mass using various, or it varies how you do that. It could be one of these formulas or other things. And then you need to find the extra moment of inertia caused by how far away you are from the center of mass. And that is just md squared. D is the distance that you're rotating from the center of mass. And m is the full mass. So I'm going to move that off to the side. And the first example that I'm going to do is one that is actually related to your book. It's example 12.13 from page 329 of your book. Constraints due to ropes and pulleys is the section. And they go through a lot of algebraic proof of this example 12.13, and I'm going to treat it a lot differently. It's kind of a mental shortcut, and if you understand it, I think it can help you out. All right, so what we've got here is we've got an object. I think it's a solid disk. Radius is equal to 2 meters. Mass is equal to 1.0 kilogram. And we have an object that's hanging at the end of the rope off of this. That mass is 2 kilograms. And it's 1 meter from the floor. And the question is how much time is it going to take to hit the floor? Now what they do, and it's a reasonable way to attack this, is they end up relating the angular acceleration of this to the linear acceleration of this, recognizing that they really both have to be the same quantity. And if you can convert back and forth between those, it's going to be helpful. So meters per second squared equals angular acceleration, which is, or radians per second squared, times the radius. So we can also think of the angular acceleration is the linear acceleration divided by the radius. Those are things you really should know. And the reason I say per second squared, which sounds weird, is it helps you think about the fact that radians is really a unitless thing. It basically is a proportion or a ratio. It's part of a circle. So degree is the same way. It's just part of a circle. Angular measurements are things which measure parts of a circle or parts of a rotation, whereas linear measurements have things, quantities specifically in the numerator there, so meters in this case. So I could think of velocity would equal to angular velocity, which is that wonky w, times r. They're supposed to be semicolons. and angular velocity is equal to regular velocity divided by the radius. Finally, position is equal to angular displacement times r. Angular displacement is equal to regular displacement divided by r. Radians times meters gives us meters. So, like I say, it's a unitless thing. At any rate, that's how they go through it. I'm going to go through it a bit different. I know I've got a lot more practice in linear measurement, so I'm going to try to make everything in linear measurement. I'm going to try to think about it that way. So in this case, if I want to find how much time it's going to take to get to the bottom there, so find time for 2 kilogram block to reach the ground. If I was thinking about just a linear thing, I'd be thinking about this. X 1/2 at squared if it starts from rest. So really what I need to do is find that acceleration. How do I get the acceleration? Well, normally I'll go back to the master of all equations, Newton's second law. It's F net over m total in the system. So in this case, you might think, oh, it's 2 kilograms times 9.8 newtons per kilogram divided by 3 kilograms. Not this time. So in this particular case, and this is not a standard problem-solving way, but it is actually pretty darn powerful if you can explain it. So in a sentence or two of explaining how you do things to an AP reader can save you a lot of time if this type of problem comes up. I'm going to call it M equivalent. We're going to assume that this is a solid disk. All right, so in this particular case then, what we've got is the net force, mg, so 2 kilograms, 9.8 newtons per kilogram. Well, this is 2 kilograms here. But this is not acting as if it's a kilogram. Because it's a solid disk, and this pull, this torque is being caused all the way out. The solid disk has its coefficient, or the mass, as 1/2, which means it's acting like it's halfway out from the center. That was kind of quick. We could treat this as a 1/2 kilogram object. So I'm going to say 0.5 kilograms. Now, if for some reason this was like a yo-yo and it was being pulled halfway out, then actually it would just be mr squared, because the torque is being created where the mass is basically the equivalent mass is acting. I've never seen the AP do that though. I've seen them have things on the outside like this, and on something like a solid disk where it's the moment of inertia is 1/2 mr squared. So in this case now, I'm going to go back, and I'm going to say acceleration is 19.6 newtons over 2.5 kilograms, and that's going to be 7.84 meters per second squared. And now it's super easy to go back and use this and say 1/2, 7.84 meters per second squared, t squared. And that time to fall down is going to end up being about 0.51 seconds. So that's my shortcut to that example. Hopefully it helps you out. What would be a good magic word? Let's think about candy. What's a good candy? Yeah, let's think about that. I think they should have chocolate. It's still March. That's okay. This is the second part of the video. This is example number 2. The first one, even though it was out of the book, I guess I called it example number 1. This is a linear speed of a solid tube of uniform cranberry paste. It rolls down a 10-meter long, 30-degree hill. The fact that I'm calling this cranberry paste tells you what time of the year we would normally do this, between Christmas and Thanksgiving and Christmas. So the key thing with thinking about this is it is an energy problem. So I always like to start that by thinking if there's no energy entering or leaving a system, and it wasn't indicated here that there was, we're going to think EI is equal to EF. So initial energy is going to equal to final energy. Well, what type of energy do I have initially? That's U grav, or potential gravitational energy. We're not talking about things with planets, so we can actually use our MGH here. And then our final energy at the bottom is going to be kinetic energy. But it's not just kinetic energy. If this thing was sliding down this whole 10-meter distance, I mean, it was so little friction that it wasn't even rolling, it was just sliding down, then it would be this. But if it's rolling, it has energy both to go in a straight line and the energy it takes to roll. So that's going to be rotational kinetic energy. So KE rotational. So the fact that this initial energy is split up into two different forms of kinetic energy at the end means it's actually going to end up going slower than if we just had a low friction object slide down. So objects that have a higher moment of inertia, such as a hoop where all the mass is on the outside, will actually finish after a solid disk, which is what this is, or a sphere. And remind me in class to do that demonstration because I think that's actually a pretty cool one. I'm not sure if Mrs. Osmond got a chance to do that last year or not. All right, so when thinking about this then, I'm going to think of this all in terms of variables, and then I'm going to plug in my numbers. The AP might have you do this just in terms of variables, by the way. So I'm going to say MGH. And notice I didn't give the mass of this because, as Garrett Cox knows, mass normally cancels out. 1/2 mv squared plus 1/2. Now because this is an angular quantity, everything has to be in terms of angular measurements. So mass, the equivalent of that is moment of inertia. Angular velocity, the equivalent of that is omega squared, or angular velocity squared. Okay, well, what do I do with that? Well, for a solid cylinder, I is going to basically equal 1/2 mr squared. Okay. And omega, we can relate to the linear speed. Well, how do we do that? That's what I posted up here earlier. The linear speed is equal to omega times r. And I don't know why sometimes they use a capital R and sometimes they use a lowercase r. I think there's probably a better way to do that in terms of your book. All right, so what does that mean? I'm going to rewrite this again in terms of all linear variables, no angular variables. So I'm going to say MGH is equal to 1/2 mv squared plus 1/2. This is 1/2 mr squared. This is omega squared times, oops, hold on, I lied. I boogered it up. So if I'm going to be substituting these in for the angular velocity, I need to show it like that. So all right, let's do some canceling. M's in every term. Don't need them. R's in the numerator here and the denominator here. So this what didn't give me the radius. It doesn't matter. It's proportional. It's kind of like how when you have objects that accelerate linearly, like due to gravitational attraction, the force increases proportionally with the mass, but the mass increases proportionally with the mass, so the acceleration near the Earth's surface is the same. Kind of similar with how this works here. we're looking at the shape that matters. That's that 1/2 mr squared. Right, so now I'm going to rewrite this, and I'm going to say GH equals 1/2 v squared plus 1/2 times 1/2 is 1/4 v squared. So 4/3 GH is equal to v squared. How do I get the h? It actually could be this distance, d sine theta. So in this case, it's sine of 30 degrees is 0.5, so that h is 5 meters. Again, the AP might give you that as a variable. When I do that, 5 times 9.8 is 49. 49 times 4 is 196. 196 divided by 3 is around 67-ish, something like that, 66-ish. Square root of 64 is 8, so it's going to be a little more than that, and it is 8.1 meters per second. So that's that example. It's still March. Anyhow, this is a torque problem. So this is example 3. We've got a 10-meter long uniform plank. What that means is its density is uniform throughout, and it weighs 100 newtons. This has a 200-newton child at the 7-meter mark. The plank is supported at the left end and at the 9-meter mark, and you want to find the upward force on each support. Now, there's a couple ways you could do this. If this was actually at the 10-meter point, it would be really nice because of symmetry, but it's not on purpose. So I've drawn the supports. They're like ropes pulling up on this thing, the left side and on the right side, although it's not exactly on the right side. And I need to draw a few other things. Drawing out torque problems is actually quite helpful. So one thing is, I know that if it's got a weight of 100 newtons for the plank, then here, at the 5-meter mark, I'm going to have a weight of 100 newtons. The baby, or child, is at the 7-meter mark, and that's got a weight of 200 newtons. At any point along this, if this is stable, there's some things we know. Mainly, we know that the object is in equilibrium, and it's in more than just regular equilibrium. It's in translational equilibrium, meaning there's no net force, and it's also in rotational equilibrium, meaning there's no net torque, because this thing isn't spinning around. You could imagine that if we had like a lot of the weight over here, way to the right of this thing might pivot and flip up. So in this particular case, things I want to remember are when in equilibrium, I'm going to say that the force up is going to equal the force down. I'm going to say that the torque counterclockwise, and counterclockwise torque is a positive torque. Clockwise torque is a negative torque. Those two would be equal. So those denote translational equilibrium. That denotes rotational equilibrium. I'm going to also note that the torque, and it's a tau symbol on your formula sheet, is equal to the perpendicular force acting at the distance from the pivot point or from the axis of rotation. And we get to choose that. Now, if we had things at an angle, I could also say that force left would equal the force right, but we don't have that here. So these are the things that I really want to keep in mind. All right, the next thing is choosing a location for your pivot point or your fulcrum or your axis of rotation. Those all mean the same thing. You could choose anywhere along here, but if you don't want to solve simultaneous equations, which most people tend not to want to do, you want to choose wisely. Here I've got an unknown force, a known force, a known force, and an unknown force. Well, if I choose one of the unknown locations, that means that, say, this force acting upward here, that's my fulcrum. No matter how much force it is, it causes zero torque. So that means these two clockwise torques would have to equal that counterclockwise torque. The same way I could choose this location as well. Now I'm going to choose this location just to be a little bit ornery, mainly because I want you to understand we always measure from the axis of rotation or from the fulcrum. It's easier to do it here because that's just 5, 7, and 9 meters away. Here I'm going to have to subtract that off. So I just want to make sure that you understand that. All right, so in this case, I'm going to set up an equilibrium equation. I'm going to say torque counterclockwise is equal to torque clockwise. So for this being the axis of rotation, this pulling upward would cause a clockwise torque. It would cause this thing to want to rotate clockwise. This would cause a counterclockwise torque because it's to the left of this. This would cause a counterclockwise torque because it's a downward force to the left of the fulcrum. If we had a downward force over here, that would cause a clockwise torque. So I'm going to look at the counterclockwise. I've got 100 newtons. The distance is at 9 minus 5 meters, or 4 meters. It's the distance from the fulcrum to that force, plus 200 newtons. That distance away, that's 9 minus 7 meters. And this, I'm going to say, is FL. It's the force on the left side. And that's going to be 9 meters away. All right. So I've got 100 times 4, that's 400 newton meters. 200 times 2, that's another 400 newton meters. FL times 9. So I've got 800 newton meters. And I like to write these down, that's these units down, because newton meters divided by meters gives me newtons. So that's going to be 8/9, or it should be around 88.8 newtons. So this is pulling upward with 89 newtons of force. Now you might ask, how do I go about solving for the force on the right? Notice it's interesting. I put the pivot point or fulcrum on the right side to solve for the force on the left side. And you might think, well, I could do this problem again, moving the fulcrum to the left side to solve for the force on the right side. And you could, but that would take a little while. So let's go back and remember this. My FUP equals F down sounds naughty. It's not, but upward force equals downward force. This is FL plus the force on the right, and that's going to equal my downward force. Well, that's 100 plus 200 newtons. FL we know is 89 newtons. So I can just simply do that algebra and realize that the force on the right side is 300 minus 89, that's 211 newtons. So that's a way to solve that. Hopefully it makes sense that this is going to have to be pulling up more because both of these downward forces are acting closer to the right side than they are to the left side. That's part 3. I should give you something else to think about. Like, what's the type of insect that you like the least? You're not allowed to say centipede because that's not an insect. But what type of insect bothers you the most? Hey, what month is it? I think you know. This is part 4. It's example 4, although I think this is an extra example in my notes on one of the last pages. It's on page 7 of my notes. At any rate, I need to draw this to give us an idea. This is something to do with the parallel axis theorem. So let's say I've got a disk here. I'm going to draw it over here. It is a solid disk, mass m, radius r. So that's R, but it is rotated at a point R over 3 away from the center. That's very odd. So let's say it's rotated there. So the whole thing goes around that little X. Hopefully it makes sense that it's harder to rotate around that point than it would be around the center. So we want to find out, first of all, the moment of inertia, or the moment, in variable form using these things. And then I put in an additional part, which is a mathematical example. Hey, here's a fun fact. The buzzards of Hinckley return in the middle of March. You might have heard about the Ides of March. I think that's from Shakespeare. I don't know. But the buzzards of Hinckley return each year on March 15th. I went up there 2 years ago. I think it was 2, maybe 3 years ago, actually, to see if I could see them. But it was a really foggy day. All I know is Hinckley, Ohio has a really good donut shop. And so basically I drove 100 plus miles, 200 miles round trip for a donut, and not to see a buzzard. But there are also some nice metro parks, I guess I saw. At any rate, let's move forward with this. All right. So, parallel axis theorem. PAT, as it's known. I don't know if it's known like that or not. I just wrote it like that. So basically, we get the I total is the moment of inertia about the center of mass plus the extra caused by it rotating off the center. Okay, so I'm going to see if I can do this up here. I is equal to, well, if it's a solid disk, it's going to be 1/2 mr squared. That part's pretty easy. What about this extra? Well, it's going to be md squared, d being the distance away from the center of mass. Okay, so in this particular case, I don't know why my m got small there. This is r over 3 squared. So notice that quantity is squared. It's not just a third, it's r squared over 9, basically. So essentially, I get 0.5 mr squared. This is going to be 1/9, which is 0.11. So the moment total will be 0.61 mr squared. That's how you do that. And again, the concept makes sense because it should be more difficult to rotate in a weird spot, but how you handle that, whether it's in variables or whether it's numerically, something you just need to think about. Okay, so what about this down here? So now I've got things where that's my system, and let's say I'm applying a 10 Newton force tangentially the edge of a disk. It could be something hanging down, it could be something pushing up, so something like that. I'm going to say that that force is equal to 10 newtons. Well, if the radius is 2 meters, then that's going to actually create, if that's acting perpendicular to the radius, it's going to create 20 newton meters of torque. But let's go through and think about that. So just like how A is equal to F net over M, alpha is equal to net torque over moment of inertia. The moment of inertia we just got, so this is going to be F perpendicular times the distance that we are. Although I think on the formula sheet it's an R, another R, because they always use R's for things. And so this is going to be 10 newtons, 2 meters, 0.61 m, which was given as 3 kilograms. That's how much stuff we've got to try to rotate. And the R is 2 meters again. So we've got 20 newtons, 2 squared is 4. 4 times 3 is 12. 12 times 0.61 is something I don't know off the top of my head. It's around 7.2. Actually, 7.26, something like that. So we'll see. 7.32. Ugh. And the units are kilogram meters squared. You might say, well, that's a little odd. Well, remember, a Newton is a kilogram meter per second squared. So that ends up being a little less than 3. Nope, hold on. .73 radians per second squared. Now, this whole thing would rotate because it's a solid object at 2.73 radians per second squared. What if you wanted to find out something like, say, I don't know, how much a spot on this edge was rotating in terms of meters per second? Well, then we'd go back and we'd say acceleration is equal to angular acceleration times r. So I would have 2.73 radians per second squared multiplied by the radius of 2 meters. So that's going to give me 5.46 meters per second squared. If this was 1 meter out, it would be 2.73 meters per second squared. If it was a tenth of a meter out, it would be 0.273 meters per second squared. So the linear velocity changes even though everywhere along the solid disk has the same angular velocity. And that's it. Thanks.